Hi all, I am Dr. K. Raghuram Mohan Reddy, Associate Professor, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. The course name is Unconventional Machining Process. Today's topic is Electropolishing Features and Applications. Right. At the end of this session, student will be able to understand electropolishing features and applications. This is the course learning outcome of the today's topic. Right. Now let us discuss photochemical milling. Okay. So before we discuss photochemical milling, let us discuss non-traditional machining processes and how the non-traditional machining processes have been classified. So classified as mechanical, thermal, chemical and electrochemical. Okay. So under mechanical, ultrasonic machining, water jet machining, abrasive water jet machining, ice jet machining. In thermal, electro discharge machining, electron beam machining, laser beam machining, ion beam machining, plasma beam machining. In chemical and electrochemical, chemical milling, photochemical milling, electrochemical milling. Okay, right. Now let us discuss electropolishing. Okay, this is the part of photochemical milling. Right. EP, in short, electropolishing. In short, EP. Okay, so EP date back to 1935 when copper and zinc were successfully electropolished by Germans. Okay, so first German country introduced EP during 1935 for the copper and zinc. Okay, so these two materials have successfully electropolished. Okay, right. Mechanical polishing entails using abrasive particles adhered to the resilient wheels of wood, felt, leather, canvas or fabric to produce smooth surfaces. Okay, let us rewind this point again. Mechanical polishing entails using abrasive particles adhered to the resilient wheels of wood, felt, leather, canvas or fabric to produce smooth surfaces. The process is used to impart a high grade finish to a surface for the sake of good appearance. So here, when aesthetic appeal is very much important, this point will be a considerable one. Okay, right. Mechanical polishing leaves a layer of distributed structure since the surface does not have the same properties of the bulk metal. Okay, mechanical polishing leaves a layer of distributed structure since the surface does not have the same properties of the bulk metal. The mechanically polished surface yields an abundance of scratches, strains, metal debris and embedded abrasives which reduce the mechanical strength. So these are the problems. Okay, so mechanically polished surface will also have some issues like scratches, strains, metal debris and embedded abrasives. Okay, so these are the considerable issues in mechanical polishing. right? Further, finishing by lapping or buffing while decreasing the surface roughness. Never completely removes the debris and the damaged layer caused by the previous mechanical polishing. Okay, so definitely after mechanical polishing, we have to go with lapping or buffing for further finishing of the surface. Okay, right. The drawbacks of such a conventional polishing method can be overcome using the non-conventional polishing. Okay, let me reiterate. We have some drawbacks in mechanical polishing. So in order to overcome that one, we have to use non-conventional electro polishing, in short EP. Okay. So in subsequent slides, wherever you find EP, that is electro polishing. Okay. So this process is basically the opposite of electroplating, where the part to be finished is the anode instead of the cathode. Okay, so it is exactly reverse to the electroplating. Okay, so here EP refers to electropolishing. This is exactly opposite to the electroplating. Electroplating. This is electropolishing. Okay, right. Current density and anode potential during EP process. Okay, what is EP? Electropolishing. Right. Electropolishing is a diffusion controlled process which takes place at the limiting current of the anodic dissolution of the metal. Okay, electropolishing is a diffusion control process which takes place at the limiting current of the anodic dissolution of the metal. Okay, right. Here figure shows current density and anode potential during the EP process. Okay, right. Here this figure shows the relationship between the current density and the anode potential. Okay, so here in y-axis current density amperes per square centimeters, in x-axis anode potential. Okay, in y-axis current density in amperes per square centimeter, in x-axis anode potential in volts. Right, here you observe carefully the various points A, B, C, D. Okay, and you make a note that here smoothing. Okay, limiting current, polishing, oxygen, evolution. Okay, now let us discuss. Right here, let us discuss here when the anode potential is 0.5, the corresponding current density would be just above 0 and below 0.5. But for anode potential at B, that is just above 1, but current density is suddenly increasing. Okay, almost above 1.7. Okay, so next, after increasing the anode potential, what is happening? The current density is lowering and constant to some extent. Those regions are polished. Okay, at limiting current. Okay, and after that point, Okay, point C, the current density is increasing rapidly, though the anode potential is increasing slowly. Okay, so this is the observation from the figure that can be noted. Okay, right. Main components of a typical polishing cell. A direct current is accordingly introduced into the part which is hung from the central electrode and is surrounded by cathodes that are negatively charged. The electropolishing medium is a liquid mixture of several acids and insoluble salts. Now look at this figure, electropolishing schematic. So here, look at this. The part is hung from the central electrode, okay, and is surrounded by cathodes that are negatively charged. Okay, so this is cathode that is negatively charged. Okay, the electropolishing medium is a liquid mixture of several, see this one, acids and the insoluble salts. Okay, so this is stirrer in order to get the homogeneous medium. Okay, so this is rack, this is workpiece which is hanging from one end. Okay, so here we are giving DC power supply, negative to the cathode and positive to the workpiece. Okay, so here we are providing heater for the operation. Right. During electropolishing, the anodic surface is subjected to the combined effects of oxygen evolution that occurs with the electrochemical metal removal and saturation of the surface with dissolved metal. Okay, so what is happening in electropolishing? During electropolishing, the anodic surface, that is nothing but work, okay, is subjected to the combined effects of oxygen evolution that occurs with the electrochemical metal removal and saturation of the surface with dissolved metal. Okay, right. A film of varying thickness is normally formed over the micro depressions and is thinnest over micro surface projections. Okay, a film of varying thickness is normally formed over the micro depressions and is thinnest over micro surface projections. Now look at this electropolishing process. Okay, how the electropolishing process is going. The electrical resistance is therefore minimum at the peaks. The surface irregularities, see here you can observe surface irregularities, resulting in the highest rate of anodic dissolution process. Okay, look at this figure here. This is anodic film. Okay, high current density area that we are supplying from the DC, low current density area, this is electrolyte, so this is cathode. Okay, under such conditions, electropolishing selectively removes microscopic peaks faster than the rate of attack on the corresponding valleys. So these are nothing but valleys. So here what is happening? Removes microscopic peaks faster than the rate of attack on the corresponding valleys. Okay, so that is the significant point to be discussed here. Okay, right. The basic surface of the metal becomes bright, clean and microscopically smooth. Okay, the produced surface possesses the true properties of the bulk metal and the true crystalline structure of the metal without the distortion produced by the cold working that always accompanies mechanical finishing processes. Okay, here the produced surfaces, okay, properties of the bulk metal and the true crystalline structure of the metal without the distortion produced by the cold working that always accompanies mechanical finishing processes. Okay, right. Now let us discuss process parameters of the EP. Okay, so already I mentioned that electropolishing, in short EP. Okay, in subsequent slides wherever you find EP, that is electropolishing. Okay, so electropolishing is affected by many parameters that have a direct impact on the produced surface quality and process productivity. Okay, these include the following: workpiece material and condition, original surface roughness, current density, applied voltage, acid type, temperature and agitation. Okay, so these are the process parameters which influence the quality and productivity. Okay, these include workpiece material and condition, original surface roughness, current density, applied voltage, acid type, here chemical, okay, temperature and agitation. Okay, so these are the various process parameters associated to electropolishing. During electropolishing, it is recommended that you use a proper electrolyte, maintain its temperature and chemical composition, and supply a ripple free DC power at the correct voltage. Okay, right. Here table 1 presents suitable electrolyte conditions and current densities for electropolishing of different metals and alloys. Okay, see here table 1 represents electrolytes and current densities of for EP of different metals. So here EP means electropolishing. Okay, so for these metals, carbon, steel, stainless steel, copper, alpha, brass, phosphor, bronze. Okay, next cupro, nickel, aluminum, magnesium. These are the various metals. For those metals, we have different electrolytes and the corresponding current densities, okay, in ampere per square centimeters. Now for carbon steel, electrolyte is 182 milliliters of HClO4, 765 ml acetic anhydride, 50 ml of H2O. Okay, the current density is 0.04 to 0.06 amperes per centimeter square. For stainless steel, the electrolyte composition is 60% H3PO4, 20% H2SO4. Okay, and 20% H2O. Okay, and next one, 37% H3PO4, 56% glycerin, 7% H2. Okay, and the corresponding current density is 1 at 120 degrees centigrade. Okay, and for copper, that is H3PO4 and current density is 0.04. Okay, and for alpha brass, it is H3PO4 Cr11 NaCr2O2, and the corresponding current density is 0.14 to 0.35 at 50 degree centigrade. Okay. Similarly, for nickel, 75% H2SO4, 0.25 is the current density. For aluminum, NCiO3, and the corresponding current density is 0.04 to 0.08. For magnesium, 37% H2PO4, 63% C2H3OH, and the current density is very low. This is 0.005. Okay, so make a note, for the magnesium the current density is very low. Okay, right. Now, applications. So applications are very important in the perspective of quality and the usage. Okay, for economical and high quality electropolishing, cold rolled metals are the most important materials. Okay, cast items usually maintain the texture of the sand mold. Okay, they have coarse grains and include alloying elements, okay, such as phosphorus, lead, and silicon, that improves the metal fluidity. Okay, usually these elements will have the good fluid properties. Okay, phosphorus, lead, and silicon. Okay, but these are having coarse grains. Such a coarse texture is not removed by electropolishing. However, the surface can be made brilliant. Okay. In general, coarse grain structure and phosphorus, lead, and silicon rich phases produce rough surfaces. Okay. Now look at this. Preparing surfaces for electroplating, which creates an opportunity for the best possible adherence. Okay. The second one, producing light fixtures of electrical conduits, outlet boxes, and medical, surgical, and food processing equipment. Okay. The second point, just I missed, producing the ultimate finish for clean room tables, chairs, and waste containers. Okay. Deburring and breaking sharp edges resulted from hand filling and honing and grinding of cutting tools. Fifth one, metallographic examination. Sixth one, removing scale or distortions caused by annealing, nitriding, carburizing, welding, or soldering. Okay. Seventh one, removing skin that remains on metals after casting or forging, which allows for subsequent machining operations with less effort, time, and tool wear. Eighth one, removing hardness and stressed surface layers, which improve the surface life of a part. Ninth application is improving adhesion for coatings such as paint and plasma spraying. Okay. 10th application is smoothing of the surface to increase reflectivity and thus creating bright appearance. Okay. Smoothing of the surface to increase reflectivity and thus creating a bright appearance. 11th one, removing burrs, occlusions, and other metalworking marks, which makes it easier to clean the surface and avoid microbiological contaminations. 12th one, micro machining of metals and alloys. 13, polishing a large number of parts simultaneously. Okay, so simultaneously we can polish huge number of parts. Along with these applications, we have some process limitations too. Let us discuss these process limitations. Okay, the process cannot smear over and cover up defects such as seams and non-metallic inclusions in the metal. Okay, multi-phase alloys in which one phase is relatively resistant to anodic dissolution are usually not amenable to electropolishing. Rough scratches are not removed even by a considerable amount of electropolishing. Okay, so for rough scratching we have to go with some other method. So that is one of the limitations of this electropolishing here. Okay, right. Metals containing a high percentage of silicon, lead and sulfur can be troublesome. Okay, usually most of the metals will have silicon, lead and sulfur, okay, which give some trouble. Right. Electropolishing is more suitable for removing small scratches and imperfections than for smoothing out any type of surface waviness. Okay. Coatings, in contrast to wrought metals, will not polish to a brightness or smoothness. Okay. The base metal condition affects the electropolishing. Okay. So here after coating, definitely we feel that the substrate or base metal will be safe, but with this the base metal condition affects the electropolishing. Okay, so we have to make the base metal as per our the electropolishing requirement. Okay, right. Next, non-metallic inclusions, improper annealing, over pickling, heat scale, large grain size, directional roll marks, and improper cold reduction leads to poor electropolished surfaces. Okay, okay, right. With this, I'm concluding. So these are the following references associated to this presentation. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.